Good morning, everyone. My name is Snigdha Sarkar, and I am the CFD Application Engineer here at KETIV Technologies. Welcome, all of you, to today's Ansys Virtual Academy session. We are continuing with our series on the Ansys electromagnetic capabilities and have with us a very special guest today, Mr. Markus Kopp. Markus is the Global Technical Manager at Ansys and has over 21 years of experience in supporting the Ansys Electromagnetic Suite. And today we will be talking about how you can use the Ansys tools for radar sensor modeling. So with that, I'll pass it over to you, Markus. Thank you so much.
Thank you, Snigdha. Thank you very much. And thank you everyone for attending today's presentation. Today I'm pretty stoked to be talking to you about some of our solutions that we have. Specifically in the antenna world. The solution we're going to talk about today is our near-field radar modeling capability. So if you're familiar with Ansys and the electromagnetics tools, you're probably familiar with what we can do with tools like HFSS. However, I think you may be unfamiliar with the totality of our solution when it comes to radar modeling. So we're going to discuss that a little bit today. And of course, when we model radars, the first thing we really need to understand is that we use radar to tell us what the environment looks like, right? We tell us where there's obstructions, we use it to tell us if there's things coming towards us or moving away from us. And basically, to do a radar simulation, we need to have a number of things. We need a radar transmitter, we need a radar receiver, and we need a full-scale environment. And this is one of the new things that we have in HFSS now, since about a year ago, is the capability to model these full-scale environments like you see currently on the screen here. And what do we see? We see a number of cars, we see traffic lights, we see street lights, we see trucks, we see roads. And what we're going to do is we're going to create a real-time simulation of this environment from an electromagnetics perspective, and we're going to create a radar image, not just a static radar image, but a dynamic radar image. So, and as I mentioned, I'm very excited about this capability because it is really brand new, and it is something that is really going to enable our customers to make better designs. So we start off with the picture on the right, which is cars and trucks moving in a street environment. We use our electromagnetic analysis tools, HFSS, and the tool called SBR, which we'll talk about in a minute, to electromagnetically analyze the scene. And then we use our built-in radar post-processing in HFSS to generate the Range-Doppler plot that we see on the left. Notice this is at 76 gigahertz, so it's a very short wavelength. And if we look at, these very short wavelengths and the scale of our street scene, you'll see that this is actually a really large, extremely large simulation. Everything here is real size, right? So the 18-wheelers are as big as 18-wheelers and cars are as big as cars. So this is a real life-size dynamic simulation. And in the end, of course, while we do use HFSS and the Ansys tools, what we're really wanting is that plot on the left that tells us all of our target objects, their relative speeds to us, to each other, and direction they're going. So when we do these types of simulations, right, there's obviously steps involved. And for us, we have three main steps that allow us to do these dynamic scenarios, right? The first step is to efficiently and accurately model a radar module that you would see inside a vehicle. And in this case, it could be a car, but we could be talking about we could be talking about radar for aerospace and defense as well. The process is exactly the same, right? The only thing that's different is frequencies. But again, you really do need to start off with the component simulation that uses HFSS, traditional HFSS like we've always used it. And within HFSS, we will do the antenna design and we will optimize that antenna array for operation at the proper frequency. And then we put it into a housing and we ensure that the operation and performance of our device is not impacted by, or has the least amount of impact due to on performance due to the housing. Now, the second step is a crucial step because we can all design antennas quite well. But what the real issue with antennas is that the environment where we deploy those antennas needs to be known, and we need to know the effect that that environment has. And that's really the in-car installation of a radar system. That's that second set of pictures you see. And if you look at the elevation azimuth plane, we have a reasonably straight, I guess, a smooth black curve, and we have a fairly jagged red curve, right? And of course, what this means is that the black curve is the operation and performance of our radar module in the absence of anything around it. And the red curve represents the behavior of our radar module in a vehicle behind a fascia. There may be metal components around it, right? There might be all sorts of metallic and non-metallic obstructions. But of course, we need to know those obstructions interfere with our performance, and that's exactly what we can do in HFSS, right? And then the last thing that we have to do is we have to post-process the information, right? So we install our antenna on a vehicle, we then move that vehicle through a street scene, and as it's moving through a street scene, we do some digital processing, and of course we do electromagnetic simulations so that at every step of our movement, we have an accurate electromagnetic description of our environment, and we use that information then during digital post-processing to come up with a razor range plot. And speaking of post-processing, right, this is all going to be done in the Ansys Electronics desktop. So the Ansys Electronics desktop will allow us to do a Pulse-Doppler radar simulation where we have a transmit antenna. It issues a series of pulses, right? If you're familiar with Pulse-Doppler radar, we know that there's going to be a delay between the transmit and the transmit of a signal and the reception of that signal at some other antenna. And that delay is, of course, our range, right? Or actually half the delay is our range. And then, of course, the frequency shift between the transmit and the receive pulses determine velocity, right? So a Doppler radar can give us two things. It can give us range and velocity. Now, in our actual post-processing, we need to do we need to have a little bit more information than just, hey, we're going to send out a signal and wait for it. We do need to specify a center frequency. So for automotive radar, it's 76.5 gigahertz. We need a resolution, specifically a range resolution, right? So if we want to have a resolution of 1 meter, we need a certain bandwidth. In this case, we can see the calculation on the right, how we arrived at that figure of 100 megahertz for range resolution. We need a range max of 200 meters. So we're saying we want this radar to be accurate for at 200 meters. So we need a number of frequency samples, right? In this case, it's 200 frequency samples. Then we can move down to velocity period, and we can see what the mathematics to derive that are. and that gives us then our delta t time steps. That will also tell us what our resolution of velocity is going to be. So we have a resolution of about 1 mile per hour, right? And then when we look at all of this information, we end up with what's called number of pulses per coherent processing interval, right? So everything here is dictated by the CPI, the coherent processing interval, and that will then tell us how many pulses we have within a processing interval. And now we pretty much have all the information that we need specified so that we can do our post-processing. So now that we know the information that we need for post-processing, let's walk through how this actually happens, right? So we have a near-field radar. It's called a near-field radar because the receivers and transmitters are within the near field of each other. And what that really is, it's an antenna-to-antenna coupling problem, right? And it's in the presence of scattering geometry. Obviously, if there was no scattering geometry, this would be a pretty easy calculation. We can use things like Free's transmission equation if these things were just in free space in the line of sight, but this is not the case. So we need to do a little bit more complicated things because now we need to look at the scattered field because that represents a return from the environment. So if we really look at this guy here, we can see that our transmitter in red, it transmits a pulse or a chirp, as they're called, and in this case we can see it's a chirp where you have a change of frequencies. So that signal goes out from our transmitter, it impinges on that car, that red car on the right hand side there. There's a reflection that is then received by the receiver. That is what we call pulse 1. Right. And again, since this is an antenna to antenna coupling problem, we could actually literally look at S21, both the real part and the imaginary part, versus frequency, in this case, our bandwidth, which is shown in the lower part there. And is literally this S parameter that we have that is going to get post-processed. Right. So we post-process this using an inverse Fourier transform. And that can then go from frequency and S parameter magnitudes. The inverse Fourier transform will transform that into a receive power versus range plot, which is shown here on the right. And we can now clearly see what the range is of this car. Right? And not only can we see the range of the car, we can actually see the range of various scattering centers on the car. We'll get back to that later, but certainly those scattering centers will be helpful in determination of what the car might be, etc., what causes these things. And we'll look at that when we look at our military applications for radars. So we do a little bit more Doppler processing from our range profiles, right? So pulse 1, we've already discussed that in the previous slide. Then we have a second pulse that is obviously, now we're going to have lots and lots of pulses up to pulse N. And all of these pulses are inserted into the range profile of a radar data matrix. So for each pulse, we have an entry into our radar data matrix for our coherent processing interval. And what we really get then is what we get on the right, which is our range chirp plot. And from the range chirp plot, we can then deduce the range Doppler plot using our FFT. Now, since we're dealing with the transmit antenna and the receive antenna, this now could be easily extended to MIMO arrays, right? In other words, where you have multiple transmitters, multiple receivers, multiple input, multiple output, right? So we have a MIMO array now, which we can do as well. And again, we would do these simulations in HFSS, the HFSS tool. Most likely, we would be eventually using the SBR solver that is within the HFSS tool. If you're unfamiliar with the SBR solver is, please let me know, and I will explain it to you at the end of the presentation. But what SBR does, it computes the antenna coupling, right? Remember, this is an antenna coupling problem, and it's between pairs of antennas. So we can go through this sort of the hard way, which is the standard N by N S parameter simulation, which would require a lot of coupling sweeps. But in SBR, we also have what we call one-way S parameters, and they're there to accommodate the one-way coupling. And it's this one-way S parameter, one-way coupling that really speeds up our radar simulation in terms of efficiency. And this is really sort of the heart of it. If you want to do these types of MIMO simulations, we are going to use SBR, and we are going to use this one-way S parameter to accommodate the one-way coupling, because this is a 100-fold speed up in time required. And of course, we can use this capability for radar, whether it's ADAS radar, aerospace and defense, military radars, MIMO communication, really any other type of application where you have one antenna speaking to another antenna. All right, so then how do we do it? How do we do a MIMO setup for a radar? And again, we've created the sensor model in HFSS, and then we bring the HFSS sensor model into the SBR tool. And it's really in the SBR tool where we create these lifelike or so moving on, we can now have different types of transmitter sweeps. In this case, we can use, again, a chirp, but it doesn't have to be a particular chirp. We can use any chirp we want. They can be different per each transmitter. And then, of course, we have our receivers, right? And all of this is done in the Ansys Electronics desktop. So then we can look at our radar frames, we can look at our sampling, we can hook it up to a local oscillator, a mixer, we can put in some filtering, and then we can do some analog digital conversion, and out will pop our radar range plot. It looks way more complicated than it is. Our radar range capability is actually quite sophisticated, and it lets you do things like this, where we can look at radar scattering center locations for each frame, right, versus ground. That will then produce the plot on the left, where we very clearly can see the main scattering centers that look like our 18-wheeler trucks, but it can also showcase or highlight other cars that are at different ranges, and even the return echoes from the light poles, etc. So a little bit more detail on our SBR solution, because this is really the highlight of it all. Is what we do is we model in HFSS. Now this is the finite element solver, the radar sensor. So what we're looking at here, that little radar array, those two transmitter arrays, the linear transmitter arrays plus that receiver array off to the right. We are modeling that and that enclosure that it is in directly in HFSS, the finite element solver, right? Once that is done, the solution to this model will then become a source for the C scenario model that is implemented in the SBR. And of course, we have to take into account whether we want to, what our chirp bandwidth needs to be, what our sampling needs to be, what we need to do to get the frequency squint. But all of these things are doable in our post-processing that is included in HFSS Ansys Electronics desktop with SBR. So it really is the combination of the FEM finite element solver in association or in co-working with the SBR solver that is included in HFSS that allows us to have these types of simulations. Now, again, I was mentioning that, you know, it doesn't matter whether we're doing automotive radar or whether we're doing military radars. The application and the design process is the same. In this case here, we have a real life environment. It's some sort of ground relief environment where we have hills and possibly a roadway or a river. We have a helicopter at a particular altitude of 17.9 meters, and we have two military vehicles, tanks, that are both at different locations and distances from our helicopter. And everything is moving. Helicopters moving, the tanks are moving, right? And we're trying to see if we can simulate this type of a scene. And obviously, again, when we look at this particular model, we are looking at a large simulation space. Something like 121 million lambda squared of area. Right now, if you want to put that up into height as well, because HFSS is a three-dimensional solver, you can very clearly see that this is going to be a huge number of wavelengths that are being solved for in this simulation. And we would not be able to do it with without our SBR add-on solver. But here's our scene. We can quickly talk about the radar on the helicopter. So it's a parametric beam far-field antenna. It has a half power beam width of 60 degrees, right? It has one transmitter, one receiver, working at 30 gigahertz. We have all of our information that we need in terms of pulse width, our resolution bandwidth, our velocity resolution, what our coherent processing intervals need to be, how many pulses per frame, and everything. Here we have a electromagnetic plot of the antenna patterns that are produced by both the transmit and receive arrays on the bottom of this helicopter. And hopefully the animation will come across, but what we're simulating here is basically 2.5 seconds of scenario time. In other words, for 2.5 seconds, the tanks are moving, the aircraft is stationary, and we're going to see if we can get this to show up on our radar plot. So you have the front view on the bottom. You can see the tanks moving. Looks like the back tank is moving slightly faster than the front tank. And then we, of course, have the top view. Now, remember, this is a coupling problem from transmitter to receiver, and this is what we're really looking at here. Is we're looking at our data from our receiver channel for the first frame, pulse number 1, right? So what we're looking at here is really the direct sampled data that would correspond to a full waveform bandwidth. And it's this data here that your signal processing algorithms is going to take and extract out the radar image. And this is what that sort of looks like. So this would be a radar range. This is not a radar range and velocity plot. This is a power and range plot. And the reason why we have power and range plots is because it allows us to see exactly where the main reflections are, and we can then look at what the distances are, and we can figure out which reflection corresponds to which tank, right? And we can see here we have some ground return, then we have the tank 1 signature, then our receive power goes back down, and then it pops back up when we have the tank 2 signature. And then, of course, we have all of these helicopter to ground reflections that pop up as well, which always need to be taken into account. So here we can see our entire scene and all of the scattering that is happening. Now here is our Range-Doppler plot for that same exact scene as before, right? Now instead of us giving us a power and the distance, it is giving us a distance and a velocity. And again, here we can see the signature of tank 1, tank 2. We can see the signature of our reflection to the helicopter, which tells us that we're at 17.9 meters elevation. So this is a helicopter signature or a self-reflection, and ground clutter return, I guess would be a more appropriate word. And then we have the round trip bounce for tank 1 and the helicopter, as well as tank 2. And then when we put the two animations together, this is what we can see. So we can look at the bottom part, we can see two tanks that are moving, helicopter is stationary. If we look at the top plot, we can see the stationary object, which is our ground clutter return, which indicates the height of our helicopter. And then we see the two radar images of the tanks. And you can see in the radar image that one tank is moving slightly faster and it drives directly beneath the helicopter. And then you can see it catch up to the other tank, the tank that is going slower. So in terms of simulation time, these are what we call fairly fast simulations, right? So for this single simulation that we're looking at here, it took 4 minutes per frame on a 4-core laptop, right? And I want to stress that this was done on a laptop with 4 cores. So you might think that 140 minutes seems like a long time, but this was done on somebody's laptop. We do use what we call our Ansys proprietary accelerated Doppler processing algorithm, which does allow us to do this in near real time when it comes to analysis speed. Near real time would be, say, 4 minutes total solution time for this exact scene if we had 35 parallel tasks, 35 cores. The nice thing about SBR simulations and these types of simulations is that they scale linearly with number of cores quite easily. So it becomes pretty easy to see that if we had enough computing cores, we could do this extremely fast. Now, some of the other things that we can look at is really the effective beam width, right? So if you have a radar antenna, and you want to know what the effect of your beam width would be, is we can have a beam width 30 degrees. We can have what I would call a fatter beam width, one of 60 degrees. And when we look at our Range-Doppler plots, we notice, right, that the signature of the one tank becomes stronger, but artifacts that are on the helicopter also become more pronounced. And that's because the beam width, as the beam width goes out, you're beginning to pick up some of the reflections off the helicopter because you're sweeping out more and more. And then we could look at that on our power range plot as well. So we can see that the 60-degree beam width and the 20-degree beam width pattern, they are actually quite different. We still pick up the tank, right? That's right here. The two tanks are still there, but we are picking up reflection from rotorcraft structure. In other words, the radar is, although it is supposed to just shoot downwards towards the ground, there's obviously back lobes and side lobes, and those back lobes and side lobes, because of the larger beam width, are now beginning to pick up reflections from the body of the helicopter, which is probably something that you want to minimize or avoid. And then, of course, the last thing we can do is we can look at scattering centers, right? As you talked before, like I talked before, when we look at our power range plot, we can pick up where the scattering centers are of our objects that we are illuminating with our radar pulse. So in this case, we have a monostatic RCS at 30 gigahertz, right? That shows some pretty bright reflections, namely at 18.7 degrees. All right, we have a spike. And of course, we could figure out what is causing that spike. If you're in the military or government labs, or if you're creating defense industry type equipment, these types of spikes need to be controlled because they're the ones that are going to show up on radar, and these are the ones we want to minimize. So being able to minimize a scattering center or a scattering spike would be of benefit, but we have to figure out what is causing that spike first. And that's when we do an ISAR or an inverse scattering analysis. So what this basically means is we can produce an ISAR image for this incident wave. And because we're putting it on a range versus range plot, we can then exactly figure out where the scattering center is and what is causing that scattering. And in this particular simulation, it becomes quite clear that the scattering centers are from the sides of the turret, right? And the features on top of the turret. And this makes sense because we have some fairly sharp corners there, and we have some fairly big objects that would generate quite a large reflection. So those are the things that we can do with HFSS and our radar modeling capability that is built into the Ansys Electronics desktop. And just as a reminder, the Ansys Electronic desktop is what contains HFSS. So HFSS always is delivered with the Ansys Electronics desktop. The Ansys Electronics desktop is where we do our Doppler post processing. It is also a fully functional circuit tool, and it is a fully functional system tool. So basically any kind of post-processing or communication or electronic circuit analysis that you'd like to do can be done in the electronics desktop that is shipped with HFSS. It is a fully functioning electronic circuit simulator. And with that, I think that's all I had to discuss today. If you guys have any questions, I'd love to hear them. If there's any details about HFSS or SBR that you'd like more information on, please let me know, and I'm ready for your questions. Thank you very much for listening.
Thank you, Markus. Thank you. That was really helpful and informative.
Thank you so much. Thank you, everyone, for listening, and I hope you have a great rest of the day.
Thank you, Markus. Thank you, everybody. Bye-bye.